In mathematics, a symmetry group is an abstraction used to describe the symmetries of an object. A group action formalizes the relationship between the group and the symmetries of the object. It relates each element of the group to a particular transformation of the object. In this case, the group is also called a permutation group or transformation group. A permutation representation of a group G is a representation of G as a group of permutations of the set, and may be described as a group representation of G by permutation matrices. It is the same as a group action of G on an ordered basis of a vector space. A group action is an extension to the notion of a symmetry group in which every element of the group acts like a bijective transformation of some set, without being identified with that transformation. This allows for a more comprehensive description of the symmetries of an object, such as a polyhedron, by allowing the same group to act on several different sets of features, such as the set of vertices, the set of edges and the set of faces of the polyhedron. If G is a group and X is a set, then a group action may be defined as a group homomorphism H from G to the symmetric group on X. The action assigns a permutation of X to each element of the group in such a way that the permutation of X assigned to the identity element of G is the identity transformation of X. A product GK of two elements of G is the composition of the permutations assigned to G and K. The abstraction provided by group actions is a powerful one, because it allows geometrical ideas to be applied to more abstract objects. Many objects in mathematics have natural group actions defined on them. In particular, groups can act on other groups, or even on themselves. Because of this generality, the theory of group actions contains wide-reaching theorems, such as the orbit stabilizer theorem, which can be used to prove deep results in several fields. Definition: if G is a group and X is a set, then a group action phi of G on X is a function that satisfies the following two axioms as G, X. Identity, X equals X for all X in X. Compatibility, X equals G, for all G, H in G and all X in X. The group G is said to act on X. The set X is called a G set. From these two axioms, it follows that for every G in G, the function which maps X in X to G, X is a bijective map from X to X. Therefore, one may alternatively define a group action of G on X as a group homomorphism from G into the symmetric group Sim of all bijections from X to X. In complete analogy, one can define a right group action of G on X as an operation X times Gx mapping to X, G and satisfying the two axioms. Identity X, E equals X for all X in X. Compatibility X equals H for all G, H in G and all X in X. The difference between left and right actions is in the order in which a product like GH acts on X. For a left action H acts first and is followed by G, while for a right action G acts first and is followed by H. Because of the formula -1 equals H minus 1 gram minus 1, one can construct a left action from a right action by composing with the inverse operation of the group. Also, a right action of a group G on X is the same thing as a left action of its opposite group Gop on X. It is thus sufficient to only consider left actions without any loss of generality. Examples: the trivial action of any group G on any set X is defined by G, X equals X for all G in G and all X in X, that is, every group element induces the identity permutation on X. In every group G, left multiplication is an action of G on G. G, X equals Gx for all G, X in G. In every group G with subgroup H, left multiplication is an action of G on the set of cosets G, H. G, R equals GAR for all G, A in G. In particular, if H contains no non-trivial normal subgroups a G, this induces an isomorphism from G to the A subgroup of the permutation group of size G, H. In every group G, conjugation is an action of G on G. G x equals gxg minus 1. An exponential notation is commonly used for the right action variant. xg equals g minus 1 xg. It satisfies h equals xgh. In every group G with subgroup H, conjugation is an action of G on conjugates of H. G, K equals GKG1 for all G and K conjugates of H. The symmetric group Sn and its subgroups act on the set 1, n, by permuting its elements. The symmetry group of a polyhedron acts on the set of vertices of that polyhedron. It also acts on the set of faces or the set of edges of the polyhedron. The symmetry group of any geometrical object acts on the set of points of that object. The automorphism group of a vector space acts on the vector space. The general linear group GL and its subgroups, particularly its Lie subgroups, orthogonal group O, special orthogonal groups O, and symplectic group SP, are Lie groups that act on the vector space knots. The group operations are given by multiplying the matrices from the groups with the vectors from knots. The affine group acts transitively and faithfully on the points of an affine space. This is in fact one way to define an affine space, i.e., saying that as a transitive and faithful action is equivalent to the formal definition of an affine space. Identity and associativity are equivalent to the definition of a action, and uniqueness is equivalent to the property of the action of being transitive and faithful. The projective linear group Pgl and its subgroups, particularly its Lie subgroups, which are Lie groups that act on the projective space Pn. This is a quotient of the action of the general linear group on projective space. Particularly notable is Pgl, the symmetries of the projective line, which is sharply 3-transitive, preserving the cross ratio. The Mobius group Pgl is of particular interest. The isometries of the plane act on the set of 2D images and patterns, such as wallpaper patterns. Isometries are in fact one example of affine group. The sets acted on by a group G comprise the category of G-sets in which the objects are G-sets and the morphisms are G-set homomorphisms. Functions f, x, y such that G equals f for every G and G. The Galois group of a field extension L, K acts on the field L but has only a trivial action on elements of the subfield K. Subgroups of Gal correspond to subfields of L that contain K, i.e., intermediate field extensions between L and K. The additive group of the real numbers acts on the phase space of well-behaved systems in classical mechanics by time translation. If T is in R and X is in the phase space, then X describes a state of the system, and T plus X is defined to be the state of the system T seconds later if T is positive, or minus T seconds ago if T is negative. The additive group of the real numbers acts on the set of real functions of a real variable in various ways, with equal to e.g., f, f plus t, f, fet, or f plus t, but not f. Given a group action of G on X, we can define an induced action of G on the power set of X by setting G U equals G U for every subset U of X and every G and G. This is useful, for instance, in studying the action of the large map U group on a 24 set and in studying symmetry in certain models of finite geometries. The quaternions with norm 1 as a multiplicative group act on R3. For any such quaternion, the mapping F equals ZXZ is a counterclockwise rotation through an angle alpha about an axis V. Z is the same rotation. See quaternions and spatial rotation. Types of actions. The action of G on X is called transitive if X is non-empty and if for each pair X, Y and X there exists a G and G such that G, X equals Y. Faithful if for every two distinct G, H and G there exists an X in X such that G, X, H, X, or equivalently, if for each G, E and G there exists an X in X such that G, X, X. In other words, in a faithful group action, different elements of G induce different permutations of X. free if, given G, H and G, the existence of an X in X with G, X equals H, X implies G equals H. Equivalently, if G is a group element and there exists an X in X with G, X equals X, then G is the identity. Regular if it is both transitive and free. This is equivalent to saying that for every 2x, y in X there exists precisely one G in G such that G, X equals Y. In this case, X is called a principal homogeneous space for G or a G-torsor. N transitive effects has at least n elements, and for all pairwise distinct x1, xn and pairwise distinct y1, yn there is a G in G such that Gxk equals Yk for 1kn. A two-transitive action is also called doubly transitive, a three-transitive action is also called triply transitive, and so on. Such actions define two transitive groups, three transitive groups, and multiply transitive groups. Sharply n-transitive if there is exactly one such G. Primitive if it is transitive and preserves no non-trivial partition of X. See primitive permutation group for details. Locally free if G is a topological group, and there is a neighborhood U of E in G such that the restriction of the action to U is free, that is, if G, X equals X for some X and some G in U, then G equals E. Irreducible if X is a non-zero module over a ring R, the action of G is R-linear, and there is no non-zero proper invariant submodule. Every free action on a non-empty set is faithful. A group G acts faithfully on X if and only if the corresponding homomorphism G-sim has a trivial kernel. Thus, for a faithful action, G embeds into a permutation group on X. Specifically, G is isomorphic to its image in sim. The action of any group G on itself by left multiplication is regular, and thus faithful as well. Every group can, therefore, be embedded in the symmetric group on its own elements, sim. This result is known as Cayley's theorem. If G does not act faithfully on X, one can easily modify the group to obtain a faithful action. If we define n equals G in G, G, X equals X for all X in X, then n is a normal subgroup of G. Indeed, it is the kernel of the homomorphism G-sim. The factor group G, n acts faithfully on X by setting X equals G, X. The original action of G on X is faithful if and only if n equals E. Orbits and stabilizers. Consider a group G acting on a set X. The orbit of an element X in X is the set of elements in X to which X can be moved by the elements of G. The orbit of X is denoted by Gx. The defining properties of a group guarantee that the set of orbits of X under the action of G form a partition of X. The associated equivalence relation is defined by saying xy if and only if there exists a G in G with G, X equals Y. The orbits are then the equivalence classes under this relation. Two elements X and Y are equivalent if and only if their orbits are the same, i.e., G, X equals GY. The group action is transitive if and only if it has only one orbit, i.e., if there exists X in X with Gx equals X. This is the case if and only if Gx equals X for all X in X. The set of all orbits of X under the action of G is written as X, G, and is called the quotient of the action. In geometric situations it may be called the orbit space, while in algebraic situations it may be called the space of coinvariants, and written xg. By contrast with the invariants, denoted xg. The coinvariants are a quotient, while the invariants are a subset. The coinvariant terminology and notation are used particularly in group cohomology and group homology, which use the same superscript-subscript invention. Invariant subsets. If Y is a subset of X, we write GY for the set G, Y, YY and GG. We call the subset Y invariant under G if GY equals Y. In that case, G also operates on Y by restricting the action to Y. The subset Y is called fixed under G if G, Y equals Y for all G in G and all Y in Y. Every Every subset that is fixed under G is also invariant under G, but not vice versa. Every orbit is an invariant subset of X on which G acts transitively. The action of G on X is transitive if and only if all elements are equivalent, meaning that there is only one orbit. A G-invariant element of X is XX such that G X equals X for all GG. The set of all such X is denoted XG and called the G-invariance of X. When X is a G-module, XG is the zeroth group cohomology group of G with coefficients in X, and the higher cohomology groups are the derived functors of the functor of G-invariance. Fixed points in stabilizer subgroups given G and G and X in X with G X equals X. We say X is a fixed point of G and G fixes X. For every X in X, we define the stabilizer subgroup of G with respect to X as the set of all elements in G that fix X. This is a subgroup of G, though typically not a normal one. The action of G on X is free if and only if all stabilizers are trivial. The kernel N of the homomorphism G-sim is given by the intersection of the stabilizers Gx for all X in X. If N is trivial, the action is said to be faithful. Let X and Y be two elements in X, and let G be a group element such that Y equals G, X. Then the two stabilizer groups Gx and Gy are related by Gy equals G Gx minus 1. Proof. By definition, Hgy if and only if H equals G, X. Applying G minus 1 to both sides of this equality yields X equals X, that is, G minus 1 hectogram Gx. The above says that the stabilizers of elements in the same orbit are conjugate to each other. Thus, to each orbit, one can associate a conjugacy class of the subgroup of G. Let denote the conjugacy class of H. Then one says that the orbit O has type if the stabilizer of some any X in O belongs to a maximal orbit type is often called a principal orbit type. Orbit stabilizer theorem and Burnside's lemma. Orbits and stabilizers are closely related. For a fixed X in X, consider the map from G to X given by GG, X for all GG. The image of this map is the orbit of X and the co-image is the set of all left co-sets of GX. The standard quotient theorem of set theory then gives a natural bijection between G, Gx and Gx. Specifically, the bijection is given by HGX X. This result is known as the orbit stabilizer theorem. From a more categorical perspective, the orbit stabilizer theorem comes from the fact that every G-set is a sum of quotients of the G-set G. If G and X are finite, then the orbit stabilizer theorem, together with Lagrange's theorem, gives this result as especially useful since it can be employed for counting arguments. A result closely related to the orbit stabilizer theorem is Burnside's lemma, where Xg is the set of points fixed by G. This result is mainly of use when G and X are finite, when it can be interpreted as follows. The number of orbits is equal to the average number of points fixed per group element. Fixing a group G, the set of formal differences of finite G-sets forms a ring called the Burnside ring of G, where addition corresponds to disjoint union, and multiplication to Cartesian product. Group actions and groupoids. The notion of group action can be put in a broader context by using the action groupoid associated to the group action, thus allowing techniques from groupoid theory such as presentations and fibrations. Further, the stabilizers of the action are the vertex groups, and the orbits of the action are the components of the action groupoid. For more details, see the book Topology and Groupoids referenced below. This action groupoid comes with a morphism which is a covering morphism of groupoids. This allows a relation between such morphisms and covering maps in topology. Morphisms and isomorphisms between G-sets. If X and Y are two G-sets, we define a morphism from X to Y to be a function f x y such that f equals G, f for all G in G and all X in X. Morphisms of G-sets are also called equivariant maps or G-maps. The composition of two morphisms is again a morphism. If a morphism F is bijective, then its inverse is also a morphism, and we call F an isomorphism, and the two G sets X and Y are called isomorphic. For all practical purposes, they are indistinguishable in this case. Some example isomorphisms. Every regular G action is isomorphic to the action of G on G given by left multiplication. Every free G action is isomorphic to G times S, where S is some set and G acts on G times S by left multiplication on the first coordinate. Every transitive G action is isomorphic to left multiplication by G on the set of left cosets of some subgroup H of G. With this notion of morphism, the collection of all G sets forms a category. This category is a graph n-deek topos.